that results in nonlinear activity prior to final failure, and this could be due to the presence of microcracks, porosity structure, but there is no plastic deformation as seen in permanent deformation as seen in plasticity. So if at any point in this force deflection curve you unload, you will come back to the zero load situation. So there is the permanent deformation. What is also characteristic is that there is this micro cracking events result in crackling noise. It's measurable as intermittent acoustic signals. Now this is very valuable information because it's happening prior to the final event, and it would be immense use if we can utilize this data in some sort of predictive modeling of fracture of disordered materials. So that's the broad question, that can we use the AE data in predictive modeling of fracture of disordered materials. Now AE has been used, AE signals have been utilized in several contexts in engineering applications. So here what I'm showing is a concrete beam which is notched, and if you see visually, then these are the crack paths, eventual crack paths that form, fairly complex but localized. But if you look at, but if you look at the acoustic picture of that, you see that the events or that occur, the damage events are occurring at a much larger span, and there is a huge process zone that is involved in making these much sharper localized cracks. So and this is also observed in the macroscopic response. If we see and the AE hits, you see a lot of activity before the peak load is reached, and even after the peak load there is significant amount of activity. So nucleation of microcracks occur at multiple sites, and the material is heterogeneous, its fracture behavior is statistically distributed. This makes it a very complex system to analyze. Now this is, so from engineering point of view, the AE data has often been utilized in location of the damage activity, also for segregation of fracture mechanisms. If there are multiple competing fracture mechanisms, then when do they start, for instance. So onset of different fracture mechanisms, that has also been of interest. Onset of crack growth, that has also been of interest. So the focus has been towards identifying fracture mechanisms or the initiation of those fracture mechanisms in the deformation history. Now in statistical physics, the interest has been the nature of the distribution of the amplitude of these intermittent bursts. And here what is shown is a sample that is of synthetic plaster. It is compressed periodically to simulate the effect of an aftershock, aftershocks, and then we look at the, what is looked at is what is the distribution of the amplitude of these events, and it is found to be a Power law with the exponent of 1.7. And the same Power law behavior is observed in multiple other, I am only talking about the in the context of fracture, as this Power law behavior is observed in various physical phenomena, but my focus will remain in the studies that have focused on fracture. So if we look at, so that was compressive, in which a cylindrical sample was compressed 5 times with some load. And here what is done is it's actually a newspaper, a newsprint paper, which is a small notch is put in that, and then when subjected to an opening mode, which doesn't really remain opening mode because paper kind of deforms out of plane also. But what is measured is again the acoustic activity at 2 different strain rates or loading rates in the remote displacement. And what is seen is that at a higher rate you see the fracture initiates, and then there is this is the force deflection curve hidden behind the acoustic signals. So you have acoustic activity prior to this here, and you have post that also. At a lower rate, there is the most of the activity occurs prior to the peak load. And what is shown here is an intermediate straining rate in which there is activity before this peak load as well as post that. And what is found is that the power law is fairly robust, and it's approximately here. It is the energy distribution. Earlier what was shown was the amplitude distribution, but they are connected. So you see the power law behavior in either of the distribution, or you can characterize either of them. So this is compressive failure of a material in which porosity has been controlled by adding graphite and also different ways of manufacturing it. And for these 4 types of samples, which differ by in their porosity from 30% to sorry, this one is the 30% to 50%, I think, I forget. But what is seen is that the overall power law exponent is roughly 1.8, and there is a weak decay of P of E for large energy for the most porous. So this one is the most porous. And then in another, so that was, this is biological material. In biological material also, for 4 different types of samples here, they differ by the age of the bone. It is extracted from the femur of a pig or pig, and the animal's age is the parameter that is different. And what is observed is that all of them exhibit, all the samples, these are cubic samples under compression, they exhibit power law behavior. Power law differs minutely, but that has been connected to the age and the porosity of the samples. So all these different contexts talk about what is the power law and the power law behavior. And in modeling, there are several models which are popular in this context of generating the avalanche statistics and the power law behavior. And they have successfully shown that there is existence of power law behavior in breakage of fibers in fiber bundle model, in the burnout of resistors in the random fuse model, and of course breakage of springs in the random spring network model. And these models have, apart from reproducing or this avalanche statistics or power law behavior, also have provided a lot of insights into various other aspects. For instance, is this avalanche statistics behavior universal across all disorders? No. So that is the you see that depending on the extent of disorder, you see different types of fracture behaviors. And this study with a fuse network, essentially you increase the current passing through the network of resistors, and all of them have a threshold, which is from this power law distribution, and when it's exceeded, it burns out and stops conducting, and you have initiation of damage there. And if the damage is such that the network stops conducting, you say it's failure. So what is seen is that for low beta, so that's one of the extremes. Low beta means you have very highly disordered material. So what you see is the red color is the spanning cluster, the largest, the cluster that is spanning the width. You see, so you could call it, for instance, like a fracture path. And for high disorder, you see that it is very ill-defined and all over the place. And what you call as the percolation type of fracture. The black dots are the other damage events which are not part of this cluster, and you have a high density of them. So there's a lot of damage activity prior to final failure, and it is a very diffused form of crack path. The other extreme is when you have low disorder, so that's high beta, when you have minimal activity in terms of damage prior to final failure, and you have a very well-defined crack surface spanning the width. And in between, so this is the nucleation type fracture where you have few nucleating events, and then there is growth of that, and you do not have independent events, nucleating events that grow independently until for a significant amount of deformation or here increase in the voltage. So this is the one which is the avalanche type, which is in intermediate disorder. So that avalanche power law behavior that was being earlier said as universal has now some conditions that it depends on the kind of disorder or the extent of disorder. Very high disorder has issues, very low disorder has issues. It's the intermediate range that we would. Based on that, this is the phase diagram in which high disorder to low disorder, if we go, we are going from percolation, avalanche type fracture to nucleation type fracture. But also in this axis is that for the same disorder, you could transition from what was nucleation when the sample size becomes, when the sample size is increased to the left, from avalanche type of behavior, you could transition to nucleation type of behavior. The power law behavior of this again is a little confusing in the sense that as you increase the disorder, so low disorder and high disorder are the blue and the black, and it's the intermediate disorder that is the avalanche type. And what is said is that that is the one which is closer to the one for the random fuse, fiber bundle model, and so that's the avalanche type. Sorry? Yeah, sure. Yeah.
Right?
Right.
So how did you put in the disorder? I may have missed that point.
Yeah, so people put in different ways. The studies that, this particular study is essentially, so this is a network of resistors, and what is the current passing through them is being increased.
I understand. So
yeah.
that is just breaking the resistors at random or
at
in a particular.
Random. Yes, from a distribution.
My point is that fracture, like instead of putting in disorder by hand like this, as of now, we also know that a fracture propagates at the tip of the fracture, the stress is concentrated, and that itself sort of acts as a propelling force to dispel the stress till the fracture opens. That's the Griffith criteria, So, I mean, what I was trying to say is that this nucleation type and the percolation type, that means that is tuned basically by the way you are putting in the resistors. But if you had allowed a natural fracture to happen, then I mean, just by driving it by the stress, that accumulates, could we have differentiated in such clear categories? That is what I was wondering. That, this is percolation type, this is avalanche, or is this only a model, toy model?
Um,
If
I'm
I don't know
hoping
if
that
I've
at the
been
end
able to
of the
make my
talk you
question
will
clear.
say that it's not just a toy model, because
No, no,
we'll
no, I'm
try
not
to
saying
simulate
that.
experiments, real experimental data, and
Okay.
many aspects of it. But yes, it's a very simplistic model in the sense you are.
But you are not taking in the stress concentration at a crack tip that is
uh,
driving a
right.
fracture.
So if I.
You are? Oh, okay, okay, okay. Then I will understand it later. So,
Yeah, I think it will come, but quickly if I answer that, here there is no pre-existing macroscopic crack per se. So Griffith's criteria is not really applicable to something. It's a disordered media, everything is intact, but the strength is distributed. Right? So when you are pulling it apart, there will be some nucleation events. Of course, the nucleation events would result in localization of, in this case, I don't know the exact mapping, but in random spring network, it will be localization of stresses and strains. Exactly. Okay. So, um, so, so that is related to the avalanche statistics. This was the fracture type based on disorder. The other very interesting line of investigations is the prediction of imminent failure, because power law, if it is universal, you can't tell the difference. Then as an engineer, we get worried that when will I know that things are going to break down, and um, it makes you nervous that it is not distinguishable. But these studies have shown that if you look at the um, so what has been done is that in the fiber bundle model, distributed failure stress threshold is applied, and this distribution is has a wide width for off critical exponent, and for a narrow near critical width to find the exponent in near critical conditions. And what is found is that from what was told earlier, which was 2.5, near critical, there's a crossover to 1.5. And this crossover also in the same study is shown to be a universal phenomena independent of threshold distribution. For variable distribution also it was shown. And then in the same study again, there was also that in the random fuse network, you see exactly the same type of crossover behavior from exponent of critical, that is 3 to 2. So there is an indication of imminent failure, which is, very interesting idea. So similar context of imminent failure, if we look at the experiments of Jiang et al. So what they do is they have a sandstone specimen. It's fairly large, so you are able to see the location of, you're able to resolve the location of the acoustic events. And so at the beginning of the compression, what you see is acoustic activity only at the surfaces where the load is being applied, which may be resulting from friction, but not in the main, the specimen per se. As the load is increased, what you see is that the source of the acoustic signals are randomly dispersed. There is no obvious correlation between the previous nucleating events. So there is uncorrelated growth of or microcracking activity, you could call it. very close to the final failure, which you can see is along this plane, you see that there is a huge localization of the next level of activities, and this whole thing has been the growth of damage has been split into early stage and approach to final failure. And as you can see very clearly, there is random distributed independent event sources, and these are associated with a larger exponent, and this correlated events are the ones which have the lower exponent. This is the acoustic activity, this is the initial activity, and then you have a band of fairly dormant kind of and then there is a build-up of energy as you approach final failure. So when they look at the power law exponents of these samples, as I said earlier, so what they do here to, so how do you measure the crossover is also a little tricky, as in what is the boundary you decide that, okay, before this I'll call off critical, after this I'll call. So what they have done is they have used time as the way to split the data, and they have found that there is a crossover for the dry sandstone that I had shown earlier from 1.77 to 1.53, and similarly for the other materials including coke. And right, so here also they are saying that whatever was reported in the simulations is also seen in experiments, and it's encouraging. Now, now looking at the same, same time series with a little different approach in terms of what you look at has been done, which is you look at the record-breaking events rather than the whole time series. What are records? Records are events, as in any sports event. The record is the previous, or the current best. So events whose size is larger than all the previous events. So the first event is always the first record, and then it kind of goes along until it meets another larger event, and then that's the new record. So this is record 1, record 2, record 3, 4, 5, 6, like that you build up. And that also presents some interesting aspects, which is the records, if you look at, which is the blue circles, they also show power law behavior. So from 2.15, if you look, which was the exponent for the, okay, I didn't mention what study is this. This is a simulation in which you have spherical particles, three-dimensional. You make a cylindrical sample with sediment and spherical particles, and the size distribution is the disorder. And I couldn't follow exactly their fracture behavior, how they have put, but the disorder, it seemed to be part of the size of the particles. And anyhow, what they report is that they see the power law behavior in the all data and the records data, but the power laws are different. Now, the other thing that they use this concept of records is to now come up with, what was earlier the strain dependent exponent. We didn't know what are the ways we could mark as boundaries. Now you have clear boundaries, record 1 to 2, whatever is in between, you can do the statistics of that, and subsequently, and you can see how these exponents evolve with the applied strain. So what was seen is that, so the x-axis is the record index, and as you go along, you see that the exponent, so maybe we should look here first. So these are the record indices, 5, 7, 9, 13, like that, and for each of them associated subsequences, the statistics of that shows that there is a change of slope in the power law behavior, and that has been summarized here, that from a high value to a low value, this is now what is off critical. Earlier off critical was this entire thing, the entire data. Now we are even splitting it to for each, between each records. And similar record statistics in coal has also been shown to result in exponent reducing from 1.5 to 1.3, and this is all experimental data where you see this transition from the exponents of the subsequences at lower k to higher k. So this is also a good in the line of investigations about imminent failure. It seems nice. So the question that we ask is that what is the role of disorder on record statistics parameters, and can record statistics be utilized in prediction of imminent failure? Right now it is being, the previous studies have shown it to be as actually the markers for taking the subsequence. Can we do something more than that? Right. So we use random string network model. We have utilized it initially for reproducing experimental data on bone, in which we find the compressive exponent to be roughly around 2. We are able to reproduce fairly well the experimentally observed failure planes. Then we have also done it for patterned two-phase materials and looked at the exponents there, but those studies are just background that we have used them. So maybe all of you are familiar, but I'll just go through the details in a brief manner. So you have the domain in which you discretize it into a lattice. We use a square lattice, and we also use, so every lattice point we connect with a nearest neighbor as well as the next nearest neighbor, and these connections are through extensional strings, and between the adjacent neighbors the connection is made through the lattice point by a torsional spring. So this allows the deformation to have both extensional energy as well as distortional bending energy, you could call it. And so the energy can be written in terms of the deformation of the lattice, and this energy is compared with the strain energy of the continuum to establish the connection between the continuum properties, elastic modulus and Poisson's ratio, with the springs and the extensional springs, torsional springs, and the lattice parameter. So this allows us to connect to experimental data in terms of not only the fracture characteristics like avalanche statistics, but also force deflection curves and prediction of even loads at which failure will occur, kind of. Right. Now, simulation steps, I will just kind of run through. We apply quasi-static tensile loading, small strain increments at the top row, boundary conditions, restrict the bottom row to move only in the horizontal direction, so the vertical direction is restrained, and because of the deformation energy stored, you have forces coming onto particles, and those particles evolve. For each increment, we bring it to static equilibrium using a dissipation factor, and the Berle algorithm is used for updating the particle positions. The acceleration of the particle is from the forces that it gets from its neighbors. So, So the spring failure characteristics are when the strain in the spring reaches a critical value. For the initial part of the study that I am presenting, I'll be using the distribution from a Pahala distribution, just like what the random fuse model of Shekhawat et al. Was. And we would like to look at the effect of disorder on the record statistics and any interesting parameters that you know we can see. So and we look at these cases just like them, and these are the density functions. So what do we see when we have so this is high disorder, beta equal to 0.1. This is low disorder, beta equal to 5. And as you can see, the load here is 0.05 or the stress at the peak load, and here you have 500 times higher than that. So this is essentially, even though the form of the curve looks similar, it's as soon as there is any strain applied, there is a rapid breakage, and they break at very small strains, and percolation type fracture is the what do you call, as expected. It is not able to sustain any load. And as we increase the beta, which is essentially lowering the disorder, the behavior from a nonlinear behavior prior peak load starts becoming very linear and then more brittle, which is expected in nucleation type of fracture. If we look at the avalanche series of these, so the first one here is just showing a typical for system size 200 cross 200. We have, so you can see that these black lines are the, how much time I'm just, yeah. So black lines are the avalanches, and the red dots are the records. So you can see that there is, yeah, 1, 2, 3, 4, 5, 6. I mean, they're too close here, so not able to see that. But you can see that this is record number 9, record number 10, and that is the associated index k equal to 9, 10. And then there is this waiting, what we are calling as strain interval, but just because, I mean, waiting time interval has been talked about, so it is just a multiplicative factor because we are applying a constant loading rate. Anyhow, so some interesting observations are that if you in terms of waiting strain interval, for the first record, as we increase disorder, so disorder is here. This is the lowest disorder. Yeah. So the lowest disorder has very high first record, and then as the records are made, it has an kind of a decay, or the waiting time interval keeps on reducing, and there is a sort of acceleration towards the final failure. So this is the waiting strain interval. You have the highest strain, this is the highest strain, that is for the first record, but subsequent records require less and less deformation, and you are approaching failure. So there is a sort of acceleration. When you look at the intermediate disorder, lowest disorder, beta equal to 0.1, has only 2 records, very few or 1 record. So we are not doing any statistics of that, but if you look at the beta equal to 1, which is the intermediate disorder, you see that the first record is made instantaneously as soon as the loading starts, and then you have the next record is also not too far away, but then the interval slowly starts increasing, and then you have a period where nothing happens, which is the longest period of wait, and then slowly it starts again becoming faster before final failure. So that is what is reflected here. The first record here has minimal strain required, which is this one, and then as you go to the next records, you require more and more strain, but the intervals become larger. Then you have the peak corresponding to that, and then you have speed up acceleration. And the one in between, so here we see a peak formation and then acceleration. Here you see only acceleration for the low disorder, and this is for beta equal to 3. You do see a peak, but the first record happens a bit later than what it was here. So, and then it's an in between these two types that you see in the extremes. So we look at, this is a single realization of each of these disorders. So if we look at the averaged behavior, so this is for system size of 200. We are changing the disorder. So for the intermediate disorder that we have, I'm wanting to call it high disorder, but since high disorder is beta equal to 0.1, so intermediate disorder here is, you see that there is a formation of the peak that we were talking about, these blue markers, and as you lower the disorder by increasing beta, that peak shifts from here to there, and then you have only acceleration type of behavior. So if we look at now individually these disorders, levels for different system sizes, we see that this peak location for beta equal to 1 that we saw here in the blue, if we increase the system size, it only lowers, but there is no change in this quantity that we are now referring as K star, which is the index of the maximum weighting strain interval, and that seemed to be independent of the system size. And this is also seen for beta equal to 3, which had already, the peak is at a lower K star, but the K star seems to be more or less largely insensitive to the system size. And for higher beta but lower disorder, the acceleration seems to be, the monotonic acceleration towards final failure seems to be also seen for all the system sizes. So now the question, the obvious correlation that we were interested in is that if we know the strain at this, is it correlated with the strain at that, which is the final strain for that sample. So we look at these correlations and see that while there is a, so what we are looking at is what is the strain at the maximum strain interval and what is the final strain and how they correlate. So these are the data points that we get. Seems to be a linear fit, but the coefficients, Pearson coefficient, checking the strength of the correlation are very weak. So you can say these correlations at best are very weak. So knowing the strain at the maximum strain interval doesn't really help in predicting fracture. What is a better indicator is if we look at the record index itself. So if we look at the record index K star where the maximum strain interval occurs, and then look at Kc and K star and Kf max, this is the maximum peak or the peak load, we see that now the Pearson coefficient is somewhat better, but as you increase the system size, it tends to deteriorate somewhat, but it's definitely a better indicator than the strain pairs, and can be utilized, and it is best for intermediate disorder when you have avalanche type. So this is beta equal to 1, where you see the highest, higher betas have very poor correlation. mutations, which is expected because of, nucleation type is even harder to predict the more brittle behavior compared to the avalanche. We also reproduce the strain-dependent exponents in terms of it going from higher to lower levels. Things to note here is that the crossover K that we saw earlier was increasing with L. While K star, so this is the crossover, it's not very well defined as you increase the system size, but the crossover from a high exponent to low exponent happens somewhere, and you can see that that transition is later and later as the system size is increased, and which makes it not a very good way of looking at it, because you are coming closer to final failure as you are moving. In contrast, K star is, we saw earlier, quite insensitive to system size, so the warning is about imminent failure if you are using K star is significantly earlier. So the second part of our my talk is about the work that we did on trying to now use experimental data and intensile fracture simulations of representative material. And is it possible to, as you saw, 5 minutes? Okay, sorry. So I'll quickly go through everything. In this, what we are trying to do is you have AE signal, AE data, and our model is random string network model, in which we are putting disorder in the failure strain threshold. And can we use the information of AE data in estimation of the disorder parameter? So we use the same model, but now we introduce a little bit of nonlinearity, a power law hardening behavior. So it's linear elastic. Beyond that, it is power law hardening. We assume quasi-brittle behavior, which means that at any point, if you are unloading, the elastic behavior is such that you reach zero load at zero deformation. And then we put some rules for that so that it happens. And spring behavior now we take from a normal distribution, and the disorder is controlled by taking the different values of this multiplicative factor, which is the standard deviation is the multiplicative factor times the mean failure threshold strain. We use a prototype material, which is a epoxy-based glassy polymer. These are the properties we determine from experiments and choose a lattice spacing appropriate for polymers. This is the experimental setup where we have the dog bone specimen that you can see here. It's an epoxy dog bone specimen. There are 2 AE sensors and the required paraphernalia to acquire AE data. We observe this kind of stress strain response, and average strength is around 57 MPa. This is what we are modeling it with. So initially we do a parametric study to see, because our distribution is now a normal distribution, what is the effect of disorder. And we see that, so this is delta small now is low disorder, delta high is high disorder. We see very similar to what we had seen earlier, that for low disorder you see nothing happening, and then there is large events and few records. As you increase the disorder, more number of events and progression towards fracture is again still in an acceleration mode. But as you go further down, you can see that the first record occurs fast, and then the next records become slower, then there is a long gap, and then there is acceleration. So disorder is resulting in um, uh, you know, it reflects in the same manner that we saw earlier. We will look in detail just after this. So what we wanted to see was that for the small disorder, how does it look when we have a record which is just before final failure? We had only 3 records there. So 1 to 2, what is the red color is what broke in this duration. Blue is what was already broken, and gray is what did not break even now. So it's still intact. So you can see that there's very